Morning, everybody. In case you weren't aware, two very critical services went offline yesterday, among others. Fortnite and Roblox. We're both down for like 3 hours, right? Yeah, and what were like, it was those two. It was like Verizon, AT&T had problems. Banks had problems. There was like a 1/3 of the internet's hosted on Amazon Web Services, and so there was Snapchat went berserk. Well, no, it went offline. It's berserk anyway. So like all this was going down. And what were the services that came up the fastest? Roblox, Fortnite. Why? They make money. What does Canvas not make? So Canvas took all day. I came in this morning and Canvas was finally working again, right? I kept trying yesterday and all that kind of stuff. So, yeah, I thought this was like a campus thing when I got here yesterday morning. And then my son texted me, goes to school in Idaho, and he texted, yeah, we can't do anything. 30,000 students on his campus, right? You can't do anything. And then I started getting reports from across the world. Europe, Africa, Australia, and I was like, I think I know what's going on. Sure enough, AWS. I hope you weren't too screwed up in your ability. Luckily for us, well, let's see, homework was due like on Saturday or something, and wasn't much going down. I hope you don't have the kind of teacher that's like, well, it's not my problem that Canvas was down. You still have to do the homework or whatever, right? Like that'd be dumb. Anyway, tomorrow is exam autopsy, okay? I'm going to try, well, actually, it's not going to happen. I have not been able to get your grades into the computer yet, and so therefore I have not been able to email anybody that shouldn't come to the exam autopsy, meaning that they got a 14. I don't remember anybody that got a 14. But anyway, I will try my very hardest to let you know if you don't have to come tomorrow, but most people need to come tomorrow anyway. And then this unit, okay, this is weird. 10, 16, and 17. So we're skipping, we're going to come back to 11 through whatever that is, okay, 15, okay? They're the thermodynamics chapters, the ideal gas law and temperature and all that kind of stuff, right? So we're gonna hold off on the thermodynamic stuff, and we're gonna do harmonic motion in chapter 10, and then we're gonna do waves and sound for chapters whatever they are, 16 and 17, I think. So just realize that the next homework is not going to be chapter 11, right? It'll be chapter 10, then chapter 16, right? So on and so forth. And then this unit again is a quick unit. You're taking your exam 2 weeks from tomorrow on this stuff, right? So we got chapter 10 today, and I think we spend 2 days on chapter 16, 2 days on chapter 17, and then we're basically taking an exam. We'll have one lab in there. That will be our standing waves lab. And so the pace continues now that you're trapped in the class and can't get out and all that, right? We're in, was this week 11? But who's counting? Oh, and we're going to cut out chapter 7, section 7 and 8, right? Okay, so what the heck is going on here? It's time for us to study emotion. Oh, and by the way, this is your final toolbox, okay? I don't consider thermodynamics to be its own toolbox because, well, thermodynamics is dumb, but more on that later, okay? But this is your final toolbox. Now, this toolbox is going to combine energy and kinematics and all that kind of stuff into a cohesive whole. But what we want to do is we want to investigate this motion right here. Now, this motion is responsible for a lot of things. And I'm not specifically talking about a mass bouncing up and down on a spring, okay? I'm talking about a motion that repeats itself. Can you think of any examples of anything in your life that seems to repeat itself over and over and over and over and over and over again? Every day, right? Like just It's just the same day. It's like living in Groundhog Day. I come to class. I do my homework. I sleep. No, it's not. I mean, there are cyclic patterns in life, but like physical motions, electrical motion, any kind of motion that just like repeats itself over and over again. This is Wi-Fi. Because Wi-Fi is wiggles, and that's a wiggle. This is a clock going around in a circle because it repeats that circular process. This is your car's engine because your car's engine has pistons in it that go up and down that turn that up and down motion into circular motion, which turns it into go motion. This is a massage chair. This is any electrical engine that turns over or oscillates or vibrates. This is so many things, okay? And we're going to start now, right, with trying to understand what this motion is doing. So just some like terminology, maybe some glossary sort of information, common words that we're going to use to describe what's going on here. So I've got a mass on a spring here, and if I get it settled down, okay, it will be in an equilibrium position, okay? This is its like natural resting position, right? In this case, gravity pulling down and the spring pulling up are kind of equal, nothing else is going on. If I pull this down, say that far, okay, and I let go, notice how high it goes? Same distance above, right? Okay. We call the maximum distance that you can get from the equilibrium, we call that the amplitude of the oscillation. If we wanted to like go at this thing and start talking about toolboxes and stuff like that, let's kind of review the toolboxes we have. We have kinematics. We have Newton's laws. We have conservation of energy. We have conservation of momentum, right? Those are the sort of the four big toolbox. Does this thing have momentum? Is it moving with velocity? Yeah. Does it have energy? Yeah. Does it have acceleration, time, and position? Uh-huh. Does it have force? Yeah. Right? It's got it all. Okay. Simple harmonic motion. This is an example of simple harmonic motion. The word simple there doesn't mean mathematically simple. Okay? Simple means that we're not going to include friction yet. Okay? But simple harmonic motion has all of those things and more, and is one of the like default toolboxes that a physicist will reach for when we don't understand what's going on. For example, what's an atom? Well, it's a nucleus and an electron and like, but what's an atom? Like, how do we model an atom? How do we mathematically solve an atom? Like, what is it? I don't know. Maybe it's a mass on a spring. So we're gonna pretend that atoms wiggle, and we're gonna see what happens. You know what happens when you assume atoms wiggle? You get quantum mechanics. You get chemistry. That's what you get, right? Physicists just went, we don't know. Let's see if it wiggles. It doesn't, but that's what fell out, okay? And so chemists even go so far as sometimes to talk about like the force that exists between atoms in a substance as like springs, like the energy that's stored in the bond is like the energy stored in the spring. There's no springs in atoms, but we still carry over that initial, we don't know what it is. Let's see if it wiggles. All right, so what's the problem here, okay? If I pull this down and I let go, right, this would be like the initial starting position of this mass, right, okay? However, I can do it by starting there, or I could do it by starting up here, right? Push it this way and let go, and it'll go down and all that kind of stuff, okay? So, like, I can have different starting positions. I can have, is the velocity of this thing constant?
No.
What's it doing at either end? When it gets here, what's it doing? Stopping. Why? How do you know it's stopping? It has to turn around, right? Okay. It was going down, and now it's going to be going up. And to be able to go from down to up, you have to pass through 0. So it's 0 at the ends, but it's moving its fastest in the middle, right? So this velocity is not constant. What's more, the acceleration isn't constant either. Okay. Let's just go straight to like the most horrible thing we could do. Okay? And what we're going to do is I'm going to write down everything for this horizontal mass on a spring, but I'm going to refer to my vertical mass on a spring all the time. Okay? I know gravity is here pulling it down and the spring's pulling it up and all that kind of stuff. But, and you just have to trust me on this, mathematically turning this on its side is identical. The setting up of a horizontal spring on a frictionless surface is a lot harder to do because we have to like support the spring's mass and like all that kind of stuff. So that's why we set up our demonstration to be a vertical mass on a spring. But it's the same math as if I did it horizontally. It doesn't matter because gravity, when we get to this equilibrium position, gravity now no longer matters. Okay? If I pull this down, what is the force? What object is pulling this thing back to equilibrium? The spring, right? The tension in the spring, right? If it's up here, the spring is now compressed and the spring will push. So this motion is not governed by gravity, it's governed by the spring. Just as if it were a horizontal spring where there's no friction and like the normal force is canceled out by gravity and all that kind of stuff, right? The only thing that matters is the spring force. Vertically or horizontally, it doesn't make any difference. Okay, so, and just some other like things to note, right? X, position of the spring. And when x equals 0, where are we? At equilibrium. You are not allowed to pick 0 anymore. It's been picked for you. The entire toolbox is going to depend on 0 being at the equilibrium position of the spring, where the spring is neither stretched nor compressed, right? And the system is just hanging out. Okay, so the force that a spring exerts on something is governed by Hooke's law. Okay? Hooke, H-O-O-K-E-S, guy's last name. So Hooke's law tells us that the amount of force is proportional to the amount of stretch. K is a constant. It's a number that tells you how stiff your spring is. So like a slinky has a really low spring constant, a really low K. And cars' springs are very stiff. They have a very high K. Jello has a very low K, right? So this K just tells you like how strong the spring is. So what are the units of force? Newtons, right? What are the units of position? Meters. So if we solve this for K, what are the units of K? A Newton per meter, right? So, by the way, we are going to use K a lot in this unit, and it's going to mean different things depending on context. I would like to take this moment to apologize to you, okay, for the fact that I will continue to propagate this terror of symbology, right? But we only have so many letters in the alphabet that we have to start recycling, okay? So K is going to be one of those letters where it's just like, what the heck is going on? Which K is this? The only way to know is by context. If we're talking about springs, it's the spring K. If we're talking about waves, it's the wave K. If we're talking about electricity, it's the electricity K. Like K gets used over and over and over again. I've been advocating for everybody to learn Mandarin, right? Because they don't have alphabet letters to say. They have pictograms, right? So like, let's just go that way. We'll have an infinite number of symbols in that point. Okay, so that's Hooke's law. It tells us that the force changes depending on how much it's stretched. When the spring is at equilibrium, what's the force? Zero, right? And where is the force the biggest? Either end, at amplitude, right? Because that represents the maximum stretch of the spring. Okay, so, oh, darn it, I keep forgetting things. That minus sign is a very tricky minus sign. That minus sign is not to be taken literally unless it's written as a vector equation, because as a vector equation, it has meaning. The magnitude of the force of a spring is kx. The magnitude is kx. It's not negative kx. The negative sign reminds us that if I pull the spring down, which way does the spring pull back? Pull. Up, right? If I compress the spring, which way does it push? Down, right? Like the spring always fights the direction that you have changed its length. That's what that minus sign means. So often you'll see me write down the force in a spring is kx. There, I don't care about the direction. I just want to know how strong the force is, right? So don't think that it's like the force is literally minus kx. That's only true if there's vector signs on it, right? If you just see kx with no vector signs, we're just talking about the magnitude of the force. That's all that matters. All right. So if I just look at the magnitude of the force here, okay? Again, didn't really want to I can put a minus sign on here if I want, but fine, I'll put them now. Yeah. The thing is here, this is where it gets a little bit goofy. The acceleration and the position will be opposed to each other. I'll show you that in a second, okay? But what's the problem here? If I solve this for acceleration, what is this trying to tell us? What's the acceleration at equilibrium? Zero, because the spring is neither pushing nor pulling, right? Okay. The acceleration will be its largest at the ends, at the amplitudes, right? So that means that the acceleration is changing everywhere. It goes from zero in the middle to maximum at the ends, and everything in between is different. The toolbox from kinematics, what was the assumption? Constant acceleration. This is not constant acceleration. This is variable acceleration. And when you have a variable acceleration, depending on position, and let's just pretend that the next 30 seconds is not something I'm going to say, and the acceleration and position are related to each other through the second derivative. Change in velocity is acceleration, right? But what's change in position? It's velocity. So the acceleration is the second derivative of the position. What we have on the screen is a second order differential equation. Now, how many of you have had diffie-Q's class? Right? Okay. Some of you are barely into into calculus. Okay. Differential equation is the equation that has derivatives in it, and you have to solve for things that are both a derivative and not a derivative. So this is way beyond our pay grade in this class, right? Okay. But I want you to appreciate the problem here, right? The toolbox I'm about to give you, and I'm just going to give it to you because you really don't want me to do differential equations in front of you. I'm good at them. I can do differential equations. I can't add, subtract, multiply, or divide to save my life, right? But I can do differential equations. I think what happened was I had to make room in my brain for differential equations, and arithmetic went out. When my daughter was like in third, fourth grade, she would be doing her homework and she'd want to race me on her like times tables and stuff. And she would kick my butt. Oh my gosh. She could do it so fast, right? And my wife would be like 7 times 7. And I'm like, and she'd be like, 49? It'd be the answer, right? Okay. And I'd be like, I'm still grappling with like, what's a number? Like, just like, and she would, my daughter would be so proud. She beat daddy, blah, 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 right? Okay. And she'd be like, oh, daddy, I beat you. I did it much faster. Do you guys have to do math facts? You have to do that thing. We had to do like 100 of them in a certain amount of time. She just like killed it, right? Okay. And I'm sitting here. I'm on the 3rd one and she's done. And so one day she's like, daddy, I'm so much better. Like, fine. And I handed her 3 differential equations. I said, when you're done with those, let me know. She's like, that's not fair. I'm like, life's not fair. Deal with it. All right. So we got a problem, right? The problem is the acceleration and position, right? Acceleration is no longer constant. So how do we deal with the motion of this system if we can't use like our kinematics toolbox, right? We need to come up with, derive, and apply our knowledge in all these different areas so that we can have equations that tell us like what the acceleration is at a certain position. Well, acceleration as a function of position is on the screen right now, right? Wherever this thing is, you can get the acceleration, right? So we have position and force. We have acceleration and position. We're going to need a few others, and we'll get to those in a second. But as a way to kind of get around having to do the differential equations, all that kind of stuff, let's like redefine some other terms, because we can take advantage of the fact that this motion repeats itself. Even though it's very complicated and the acceleration's not constant and all that kind of stuff, we can use some terminology that will help us. This mass on a spring has a period. We've run into period before, the amount of time it takes for a satellite to go once around in its orbit. When we did the pendulum lab way back at the beginning of the semester, where we measured the period of the pendulum to find little g, that period was the time it took to do a complete swing back and forth. The period of this mass on the spring is the time it takes to go from where it started and then get back to where it started, right? Okay, so the period here looks like it's about a second, right? Maybe 1.3 seconds, okay? So that's a period. I could start it up here. What would the period be if I left it up here? What would the motion have to be to do a complete period? It would have to go down and come back up, right, to where it started. That would be a complete period. If it starts in the middle, this one's even trickier. Let's say I push it up, starting here in the middle, right? And I go up like that. The complete period would be going up, coming all the way down, and then back up to the original position. It's not the fact that it returned to exactly the same place. It has to return to the same place and velocity. And what did it start with? What velocity did it start with? Positive or negative? Positive, right? But as it goes up and comes back down, now what's the velocity? Negative. That's not the same starting condition, right? So a full period is bottom, top to bottom, or top to bottom to top, or equilibrium, top, all the way through to the bottom, back to equilibrium. Those would all be period. And we use T, capital T, again, for that symbol, the time it takes for one complete oscillation to happen. The inverse of that is how many times it oscillates in 1 second, and that's called the frequency. If this thing bounces up and down 2 times per second, which it's not doing right now, but let's say it did, right? Then how many cycles happen? I said it bounced up and down twice in 1 second. How many cycles did it do? 2. And we would say its frequency is 2. 2 watts. Well, if period and frequency are inverses of each other, That means that frequency is the inverse of the period. And what's the units of period? Nope. It's time. Seconds. Okay. And what's a 1 over a second? We call that a hertz. Okay. And I know you've heard of hertz before. Okay. A lot of times when people are trying to sell you a computer or something like that, they'll tell you the speed of the processor, and it'll be measured in gigahertz. Okay, or maybe memory speeds or phone processor speeds or whatever, right? They'll mention gigahertz. What's a giga? 10 to the 9. It's a 1 billion, okay? So a computer processor running at 4.5 gigahertz is doing 4.5 billion computing cycles per second. Now, a compute cycle can be a lot of different things, but let's just pretend that a compute cycle is adding two numbers together, right? Add two numbers together, that's one cycle in the processor. So how many additions are taking place every second? 4.5 billion of those every second, right? So when they say that like the phone in your pocket is like 1 billion times more powerful than the computer that went to the moon, that's what we're talking about, right? The computer that went to the moon had a frequency that was measured in like seconds, right? Like the frequency was like, I think it was like 3 to 10 hertz or something like that, right? So it just took a while to do calculations, right? The phone in your pocket is doing them at billions of calculations per second, cycles per second. So a cycle can be a calculation or it can be something else. But this is not a computer science class. Okay, so we got frequency, we have period, okay, as definitions. I'm putting the equations of motion in the boxes here for us, okay. Here's some others that I'm just gonna give to you as a free gift. Okay, operators are standing by. Please don't ask where they come from. Please. For your own. What did I just say?
I genuinely want to know.
Okay, well then come to like tomorrow after the exam autopsy and I'll torture you with differential equations. Okay? Because you really, it's a differential equations thing. The maximum speed that this mass can have while it's bouncing up and down on the spring is the amplitude times omega. Uh-oh.
That's not rotational.
Ah. Say that again really loud.
That's not rotational.
Oh, it is. Oh, it is. I lied to you. I did it on purpose, so it was an on-purpose lie, okay? But I did it to protect you, okay? But here's the truth. What were the units of omega back in rotation? Does anybody remember? It was an angular velocity, right? A radian per second. Radians have no units. This is actually not a hertz, because a hertz is a linear frequency, okay? But omega has very close to the same units as frequency, doesn't it? Okay? Omega is angular frequency. It's not angular speed. I'm not sorry for my lie, okay? Because back then, if I had dropped like this idea of frequency on you, you're already like, about rotation, right? So it was easier to just call it, oh, it looks like a meter per second. It's a speed, right? Okay? The thing is, for anything going around in a circle, what's it doing? This is a circle. A circle is a spring. They're the same thing. I've got some slides. I'll try and show that to you in a little bit. Okay? But omega, right, comes back. not as angular speed, but as angular frequency, which is basically the same thing anyway. And the Google Translate, to get between frequency f and angular frequency omega, is 2 pi. So omega is equal to 2 pi f, right? That's how you get the radians back in there, right? To make the angular crowd happy. However, again, don't ask me why, omega can be found if you know the spring constant and the mass that's in the system. This is getting weird now, right? We can find this angular velocity that's no longer angular velocity, it's angular frequency. But that angular frequency now depends on very real properties of the system. Yes, true. Okay. What are the units of the square root of k over m? Don't think about it.
1 over 7.
It's radians per second. Because it's omega. Okay? Just believe. Just trust me on this one. You don't want to know. You don't want to know. As beautiful as differential equations are, I like them so much better than I like calculus. But as beautiful as differential equations are, you don't want to have that burden of knowledge. All right, so back to maximum value. A max, the maximum acceleration this thing can have, amplitude omega squared. Okay. Let's see. I think that's probably enough for now. Okay. Everything in the box, very important. Okay. So there's something you need to know about this toolbox. Okay. All the other toolboxes were open, unlocked. You were free to reach into them. But this toolbox has a key. The simple harmonic toolbox you need to unlock. You need to find the key first, usually, so that you can then use all the other tools in it. What do I mean by that? Have you noticed what each of these equations has in it? Look carefully. For example, k over m. We can rewrite this one as a equals negative omega squared x. What keeps cropping up? Omega. If you can find omega, you can find anything. Okay? Omega is what unlocks this toolbox. And so usually the problem isn't so much the problem as it is what the heck is omega. And we've got to sort through what the problem's telling us to try and figure out what omega is. If they give you a spring constant and a mass, you're home free, because how are you going to find omega? Square root of k over m. But what if they only gave you a period? Can period give us omega? Yeah. Right? Because we can take this, right? And this is so frequency is omega divided by 2 pi, isn't it? If I solve that right. And so over here, that means that period is equal to 1 over omega over 2, or 2 pi divided by omega. Right? Just another way of finding the period. Right? So omega's the key. Find omega. You can find anything else you want to know about anything that's bouncing up and down or right and left on a spring. This is why circles and springs are the same thing. Okay? This is like a thought experiment. We can actually do this one physically. It's a little bit difficult to set up. But if you get a turntable, like a record player, okay, and you put an object on that thing and you just set that object going around and around and around, and you just get some light and you're looking at the shadow, right? Edge on, right? You're looking at this shadow. Then what you would see is something moving back and forth like this. Well, what sorts of things move back and forth? Okay? It's the same motion. Something moving in a circle seen edge on is exactly the same motion as a mass on a spring. And we can track the position of like where we are on that circle with our rotational kinematics. We can track that onto where it is like on the shadow on the screen and track that and precisely align it with what this thing is doing. Like, for example, when the shadow is at amplitude, well, what's the amplitude of this circle? It's the radius, right? Okay. And so like we can continue to like map circular ideas onto simple harmonic motion because circles are simple harmonic motion. Circles are springs and springs are circles. To a physicist, they're identical systems, okay? Because they'll behave the same way. They have frequency, they have acceleration, they have all these different things that are going down. All right, this was supposed to be a view from a bungee tower, but the video's not working, so we'll go back. We'll just do the problem, okay? Anybody done bungee jumping? Willing to admit it? No? It's on my bucket list of things to do. I have done skydiving, and now I just need to figure out how to go do bungee jumping. So, but it won't happen this summer. This summer, too many other things are happening. All right, so what do we got? We've got bungee jumper. Okay. What does bungee jumping have to do with simple harmonic motion? Right? The bungee jumper okay, so when the bungee jumper jumps, right, starts up here, is the bungee cord stretched at all? No, right? So what's the bungee jumper going to do first? What? The bungee cord's not doing anything, right? What is this motion? This is free fall. We know how to do that, right? Okay? So the bungee part, the part that is simple harmonic motion where the bungee cable begins to stretch, right, only happens after we have hit the equilibrium position, right? That's when the simple harmonic motion part begins, okay? So we can take advantage of what we know about free fall and all that kind of stuff to figure out what's going on here. Now, again, I told you that to unlock this toolbox, what do we need? We need omega, right? And the problem is trying to give us some hints about what omega might be, okay? Notice that they tell us, okay, in the static case, so they're just hanging from the end. This is not them jumping off, right? This isn't the dynamic, right, slowing them down or making them speed back up again or anything. They're just hanging the jumper off of the bungee cable. It's like my mass on a spring. Like the cable is like doing that, right? But if we then put the jumper on the cable and just statically hang them, it tells us how much it stretches, right? So is there anything in our toolbox right here that we can use maybe to figure out omega? They've given us the mass of the jumper, and they've given us the stretch in the spring or the bungee cord. What do we need to be able to find omega? We need a period, we need a frequency. They didn't give us any of that. Ooh, X? Okay, where does X show up in any of this?
The force and acceleration.
Shows up in acceleration as a position, right? And it also shows up in the force over here, right? So, I mean, they didn't give us anything about acceleration. This is just the person's hanging there, right? They're not doing any of the acceleration zero, right? So that doesn't help us. So about the only thing we got left is Hooke's law up here, right? Okay. And what could we find from Hooke's law? If we know the position and we know the weight, we can find the spring constant, can't we? And once we know the spring constant, and because we know the mass of the bungee jumper, what can we now find? Omega. Right? So this is what I said. This toolbox is locked, right? And quite often the hardest part is figuring out the key, right? What do I need to do in order to find omega? You don't always have to find omega, but like 99% of the time, you have to find omega. So let's see, what can we do here? We know that when and sometimes a little picture helps, right? Okay, so there's the bungee cable, and there's the bungee. I don't know why they're hanging upside down, but they are, okay? When they're just hanging there, right, X is equal to 5 meters, right? And what's the force equal to? The weight of the bungee jumper, right? 70 times 9.8 if we're on Earth. I'd like to go bungee jumping on the moon. I think that'd be fun. All right, so we can then use Hooke's law. Notice I'm not writing the negative sign this time, right? I don't care about directions here. I just want to know what K is, right? So K will be the force divided by X, which is mg divided by X, which is 70 times 9.8 divided by 5, which I don't know.
137.29.
Yeah, I do. Yeah, as soon as you said it, I saw it on my page. I should ask more often. Okay, thank you. Brandon coming to the rescue. Okay, so there is my force constant. Okay, and from that force constant, what can we find? We can find omega. Okay, so omega is going to be the square root of k over m, which is the square root of 137.2 divided by 70. 1.4. 1.4. That's what mine says too. And what are the units of omega? Radians per second. Not a velocity, an angular frequency. Okay. So where have we gotten? We've gotten to omega. Omega unlocks everything. Now we got to figure out just how the key is going to help us. How long does it take for the bungee jumper to return to the equilibrium position of the bungee cord? Okay. So what the heck is happening here? We have a bungee jumper that starts at maybe the top of a tower, right? And they're going to fall through a distance of 20 meters and nothing's really going to happen, right? The bungee cord isn't stretching, it's not doing anything, right? Okay. And then, so they jump off, right? And then they get to the bottom of their stretch. And what does that represent? Getting to the bottom of the stretch. What have they just reached? The most stretch the bungee cord is going to be is when it is at an amplitude, right? Okay. And then it's going to start coming back up. They want to know how long it takes for the bungee jumper to return to the equilibrium. So they want to know the time it takes for the bungee jumper to go down and back up. We know omega. What things in the toolbox are about time? Period and frequency. Right? Those are the things that have time in it, right? Do my middle equations have time in them? No. Not really, okay? These don't. These are really my time equations right here, aren't they? Okay? So, can we use that to our advantage? Now that we know omega, can we find the period? Mm-hmm. Yeah. But how is that going to help us in our bungee jumping problem here? How much of a period has the bungee jumper done? So they fell, started stretching, went to an amplitude, and came back to the equilibrium. How much of a period is that? It's half. You were right the first time. Okay? Because what would a full period be? Equilibrium to bottom, all the way to the next amplitude, back to the center. Now, to be clear, a bungee cord only does half of a period. Why? Does a bungee cord push? No, it only stretches. It only has tension in it, right? Okay. And so what's going to happen with the bungee cord is it'll stretch down, go to amplitude, come back up, and from this point up, it's free fall until it gets back to the equilibrium position. Then it stretches, and then it's free fall, and then it stretches, right? So the bungee cord only ever does half of a period before it reverts back to not being a spring anymore. So if we can find the period and divide that number by 2, then we know how long this bungee jumper, right? How long it takes the bungee jumper to get from equilibrium down and then back up to equilibrium. They're not going to stop there. They're going to go up and free fall and go, right? All right. So we know omega. The period is 2 pi. Was that what it was? I don't remember anyway. 2 pi over omega. 2 pi divided by 1.4. 4.5. Seconds, right? This is a period. I'm doing standard units, and so I'm going to get seconds back out again. So 4.5 seconds. Is that the answer? Do I box that one, throw it into y to the plus? No, I've got to divide this one by 2, right? So is that 2.25? 2.2, better be 2.25.
Well, the original answer was 4.48.
I hate numbers. Okay? So we unlocked the toolbox for the stretchy part of the bungee jump by finding omega. We then looked at what they wanted me to find, right? Okay, so could we determine how much the bungee cord stretches? Like the maximum stretch of the bungee cord. What are we now solving for if we want to find the maximum stretch of the bungee cord? The amplitude. Is there anything in here that can help us find amplitude? Vmax and Amax have it in there, right? Okay. But then we'd have to know Vmax. Well, where does a simple harmonic oscillator have its maximum speed? Hint, it's not at the ends. Because at the ends, it's turning around. It's stopping at the ends. So where's its maximum speed? At the middle. How do we find out how fast the bungee jumper is going when he begins to stretch the bungee cord? Square root of 2gh. It's free fall problem. Use kinematics or conservation of energy. I don't care. How fast is something going when it falls through a height h? Square root of 2gh. The height's 20, right? That's where the bungee cord begins to stretch, right? So I can know Vmax. Once I know Vmax and omega, I can tell you the amplitude. Do you think it's really important to know what the amplitude of the stretch is for a bungee cord? Yeah, why? You don't want them to hit the ground, right? So you want to put in safety margins and all that kind of stuff, right? So it's important to be able to run those calculations and know. I happen to know that bungee cord manufacturers, when you buy the bungee cord, they send along a sheet that is they did measurements on the cord, and they say for this amount of weight, this much stretch, right? So for if your passenger is 250 pounds, this is how much stretch you can expect in this cord, and then they can know if they're hanging it off the correct size tower or whatever. So, and they've calibrated the bungee cord. And as long as the person can read who's setting it up, we're in good shape. All right. I can guarantee you if I ever did this, I would be doing a lot of reading. I'd walk up and say, I would like to see the calibration documentation for your bungee cord. Thank you. And that's probably when they'd say, we're not letting you on this thing. All right. Yeah, we're doing good. If I pull this down and just hold it here, does it have energy?
Yes.
Uh-huh. Right? Where's the energy stored? In the spring. It's not kinetic because it's not moving, right? It's potential. No? The horror hasn't, you haven't figured out how bad this, okay. Here's the potential energy of a spring. It's 1/2 kx squared. I'm not responsible for this, the fact that this looks like kinetic energy. It's not. It's potential energy. So it's units of joules, right? If you put K in newtons per meter and you put the position in a meter. But what's the potential of a spring when it's not stretched? Or like when it's at equilibrium, neither stretched nor compressed? How much potential energy does it have? 0. Where is its potential energy the biggest? At amplitude, the biggest it can ever stretch. That's where the potential energy is going to be the biggest. So if the potential energy is the biggest at the bottom and top, okay, and it's how fast is it going down here at this amplitude? 0. So how much kinetic energy does it have here? 0. So when it gets to an amplitude, all of the energy is potential. So where does the kinetic energy, where does this mass only have kinetic energy? Not at amplitude. Where is the potential energy of the spring 0? At the middle, right? So we go from a situation of maximum potential energy to all potential energy to a situation of all kinetic energy. If it had 10 joules of potential energy down here, how many joules of kinetic energy does it have right here? 10. Energy must be conserved. It's just we're trading between potential energy in the spring and kinetic energy of the mass, right? So maximum kinetic energy, 0 potential energy, but at either end, it will have maximum, it'll be all potential energy and 0 kinetic energy. And in between, if it has 10 at the ends and it has 10 in the middle, what does it have halfway to a amplitude? Also 10. It's just now it's split up somehow between kinetic and potential energy. So what did we learn from all that? Not that yet. Quiz coming up. Get ready. The total energy. So the elastic potential energy is 1/2 kx squared. But the total energy any oscillator can have at any given time is a combination of its kinetic energy and its potential energy. Okay? But this total can be 1/2 Ka squared when it's all potential energy and no kinetic energy. And it can be 1/2 mv max squared. Now, that means that I can do a 1/2 Ka squared, the total, is equal to 1/2 mv squared plus 1/2 kx squared. In other words, this is the most energy it can have, and that energy can be split up between kinetic and potential energies. I'm looking at this thing going, I can get some wisdom out of this. First of all, best thing to do in the world, get rid of those dumb halves. Right? Can't get rid of the squares because they're all the same. They're all different. They're not all the same. It's an a squared, it's a v squared, it's an x squared. I can't just do that, okay? What I can do is do a little bit of clever manipulation, I suppose, right? I can do Ka squared minus Kx squared over here equals mv squared. And I can I'm going to go mv squared first. I'm going to factor out a k, a squared minus x squared. And then I'm going to take my v and I'm going to take my m and divide it into both sides. Squared. And then I'm going to take the square root. What's the square root of k over m? It's omega. And then I'm left with the square root of a squared minus x squared. Okay, what is this thing sitting in the box? That's something you want to add to your toolbox. Because what does it give us? velocity at any position, right? So we have an equation that gives us acceleration at any position. This one will give us our velocity at any position. Still, like a nice handy thing to have if you want to know how fast a simple harmonic oscillator is moving anywhere in its oscillation. So let's just double check and make sure that this equation acts the way we expect it to. What happens if our position is amplitude, like we are at the maximum stretch? We put a in for x. What's a squared minus a squared? 0. What's the square root of 0? 0. What's omega times 0? 0. What's the velocity? 0. And do we expect the velocity to be 0 at the amplitude? Yes. What happens if we put in x equals 0, or right in the middle of the motion? What's a squared minus 0? A squared. What's the square root of a squared? A. And what's omega a? It's V max. Do we expect the maximum velocity to be at the equilibrium position? Yes. So this works at the extremes. I expect it to work everywhere else. Physics. All right. And the mathematicians just, they die when physicists say stuff like that. All right, let's do a quiz. All right. Sorry for the fake out on the quiz. Conservation of energy. Work non-conservative. Energy final minus energy initial. What are all the kinds of energy we can have now? mv squared. 1/2 mv squared. Right? What else? 1/2 I omega squared. The rotational one that everybody wanted to forget. Okay. And some of you forgot on the exam. mgh for gravitational potential. And now 1/2 kx squared. Right? Those could all be there at the end, right? The final position. And the same thing goes for the initial energy, right? You can have all those kinds of energy. Heaven help you if your spring is rotating. We won't do that to you. Okay? But the point stands, right? When we find an energy, we just add it onto this conservation of energy statement, right? When we get to electricity in physics 2b, we're going to have electric potential energy. Guess where it goes? It goes right here. Okay? It goes into the list. Okay? Magnetic potential goes into the list. Chemical goes into the list, right? Like it just, we can keep adding anything that's a conservative force. We can just keep adding to this list. Okay? So, with that in mind, right? Let's see if we can't tease out some information about what's going on in any oscillator. This is scary because what are they asking us to find? How many boxes, how many parts would there be if this were a Wiley plus question? 1, 2, 3, 4, 5, 6, 7 boxes. Right? There would be 7 entries on just this question, right? In other words, find everything, right? Find everything there is to find about this oscillator. How are you going to do that? Where do you start? How do you unlock the toolbox? You unlock it with omega, right? So, is there anything here that's telling us about omega? What's 0.2? It's a distance. What can we find if we know mass, force, and position? Close. Not quite yet. To find omega, we either need to know something about the time, the period or frequency, or we need to know square root of k over m. We have m. Do we have k? How do we find k?
Hooke's law.
Hooke's law. Right? K is going to be equal to the force, 20 newtons, divided by 0.2. I should be able to do that in my head, but I can't. I have no idea what that is.
400.
Is it 400? I don't have any of my notes.
100.
I was going to say one. Yeah, that sounds a little bit better. Of course I did. I don't know why I don't have this one in my notes. 100 newtons per meter. Okay, so now that we know K, can we find omega? It's 100 divided by 2, so it's the square root of 50, whatever that is, I don't care. Okay? Square root of 50 radians per second. We have omega. We now know everything. Everything we could possibly ever want to know about this system, we now know it. It's just a matter of calculating it, right? How do we find the spring constant? We did that already. Done. It was 100 newtons per meter. Frequency. How are we going to find the frequency of this system? We know omega. Frequency. Omega is equal to 2 pi times f. So f is going to be omega divided by 2 pi. So this is the square root of 50 over 2 pi. Done. How are we going to find Vmax? What's the only equation in the toolbox that has Vmax in it? Vmax is equal omega times amplitude. Okay, well now we need to know the amplitude. What's the amplitude? Is now released from rest with an initial position of 0.2. This thing was pulled down 0.2 and let go. What's its amplitude? 0.2. So that's the square root of 50 times 0.2. Whatever that number is, I don't care. What's A max? Omega squared times that. It's 50 because it's square root of 50, and you square it, and 50 times 0.2, whatever that number is, I don't care. What's the total energy? No, well, you could do it that way if you wanted to go the long way. Yeah, we better write that down as part of the toolbox, right? Add these equations to your toolbox. Okay, A squared. Right? So there's my total energy. So it's 1/2 Ka squared, which is 1/2 times 100 times 0.2 squared, whatever that number is, I don't care. Okay? Speed and acceleration of the object when it has a certain position. Well, what's the speed of something at a certain position? It's omega times the square root of a squared minus x squared, right? So this is going to be omega, the square root of 50, times the square root of a, 0.2 squared, minus 0.067 squared. Whatever that number is, don't care. A max, A as a position, function of position is omega squared x, minus sign on the front if you want. And so that's 50 times 0.067, which is a number, I don't care what it is. So, how do you find or know everything about a simple harmonic oscillator? Find omega. Once you have found omega, it's simply a matter of plugging and chugging into whatever they're asking you to find. And you can know everything. What's the period of this thing? Well, now that I know the frequency, now that I know omega, it's 2 pi divided by omega, right? What kinetic energy does it have at 0.067? Well, it's just 1/2 kx, whatever, right? Like it's all there. It's all there, okay? This is why physicists love this toolbox, okay? The algebra is easy. The problem has been solved for us, right? All the differential equations and stuff I hid from you, the derivation of this toolbox, it's all done. Any oscillator does this. If we can find omega, we can get it. We will go so far as to turn anything into a spring if we can. Okay? Like the pendulum. Back when we did the lab, okay? Lab 3. 2 pi square root of, I think it's L over G, right? Okay? That simple pendulum equation came from treating the pendulum like a spring, finding omega for that system, an effective spring constant. Like physicists will get so desperate that we will just invent springs that don't exist. And we'll find something that acts like the spring in the problem, or find that acts like omega, and once we've got it, we'll run with it, and simple things will fall out. Why? By the way, that's the simple pendulum, a mass on the end. If you have a pendulum that's got moment of inertia in it, I think it's moment of inertia divided by mgl, like that. That might be slightly off. It doesn't matter. We won't ask you to calculate with it. But why would you want to know the period of, say, this meter stick as it swings back and forth? Why would that be important to know at all? What is this? This is my leg. Now, my leg happens to be a double pendulum. It's articulated in the hip and the knee. But why would you want to know the period that your leg does as it does its simple harmonic motion while you're walking? Does anybody know the term for how a person walks, like how you describe a person's walk? Their gait, G-A-I-T, okay? Why is a person's gait important? Everybody's got their own individual gait, okay? And when something has gone wrong with one of the limbs, maybe you sprained your ankle, maybe you're an amputee now or something like that, okay? Anybody that's ever seen somebody with like a boot on their leg or a really bad prosthesis, you'll see their walk, right? I'm kind of over-exaggerating here, but their gait isn't normal, right? It's not smooth. There's like two different omegas happening here, right? Okay? So quality of life for an amputee is huge if you can match their gait, right? If you can figure out the natural frequency that their legs would move, right? You design the prosthesis to match that natural frequency, that natural gait of their motion, then a person can go through life without causing undue stress to the hip joint or anything else. There was an incredible story that came out of the tragedy of the Boston Marathon bombings. One of the people that was injured in there was a ballerina for the Boston Ballet. She lost her ankle due to shrapnel. And she thought that she would never dance again, like not at the level that she had been dancing, right? Well, the nerds at MIT decided that that wasn't a good answer. And so they sat down and started designing a prosthesis for this ballerina to replace her ankle, right? Ankle and foot. And they were able to tune this prosthesis to her natural gait so that she, within like 8 months after losing her ankle and foot, she was returning to the ballet and able to be on point and had all of the balance and everything that she needed to be able to happen. And that work that they did has made its way into prostheses for most people, right? Being able to have articulated joints and motorized joints to be able to do what it needs to do, right, at the proper frequencies. Like, it's absolutely incredible what you can do when you understand how things swing. I asked for pictures from the internet, like of people, things swinging, right? And so, of course, it came up with a bunch of white children. So I tried representation, right? Does this dog look happy to you?
Not really.
Yeah? Okay. You can never really tell with dogs unless, the only way you can tell if a dog is happy is by watching its rear end, right? I mean, some dogs have just happy faces and some have sad faces, but a sad-faced dog, if their rear end is, which by the way is a simple harmonic oscillator, okay, then you know it's happy. Anyway, right? What happens when you force a system to oscillate at the frequency it's designed to oscillate at? Well, what you get is the swings, okay? Think about the swings. You go to sit on the swings, okay? And what do? You start like kicking your legs, right? And pulling, right? You kind of push back off the ground to get the swing going, right? And then when is it that you do the kick and the pull? At like what point in the motion? It's kind of like you've swung back, right? And then as you turn around, that's when you add the energy, right? If you are pushing a kid on the swings, okay? You're sitting here, right? You're pushing the kid, right? When do you push? I know this sounds weird, but when do you push?
When they start moving.
They start moving away from you, right? And then they'll come back, and just as they're turning around is when you add the energy, right? Okay? You don't do it at random times. You don't push the kid here and then run over here and push the kid here, right? Okay? Why? Have you ever watched a kid try to learn to swing? What do? You gotta see. Right? And then what do? Right? And they just can't, right? They don't understand that you need to time it correctly, right? But pretty quickly, if you just show them what to do, they'll just get this natural feeling for when it is you're going to do it. So as an adult, try this next time you're near a playground, okay? Go to the playground, kick all the little kids off. You're bigger than them now, okay? And sit on the swing, okay? Tell them you're doing physics homework. Sit on the swing, okay? And then start swinging. Get a good swing going, okay? And then carefully start doing the push-pull at random intervals. Like try to do it like when you're at the very bottom of the swing. If you try it on the other amplitude, be careful. You might fall out, okay? But if you start like pushing and pulling at random spots in the swing, your amplitude will die and you'll end up not having any fun at all. To get that amplitude to build up, we are forcing the oscillator. We're adding additional energy, and this causes something called resonance, okay? I wish this video was working. I found this video of a dad on the internet, and he's pushing both of his kids. He's like, boom, 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 and like they're oscillators, and he's an oscillator. Like, he was amazing, right? This is full dad points right here, okay? But like, when you get the frequency, if you push and you drive the system at the frequency it wants to oscillate at, you get this thing called resonance. Resonance is the increase in amplitude of the oscillation when you push it at the frequency it wants. Everything has its own natural frequency. Every structure, every airplane, every car, the muscles, the bones in your body, they all have frequencies that they want to vibrate at. And if you vibrate them at that frequency, the oscillations will build and build and build, okay, until usually failure happens, okay? For airplanes, this is really important. There was I think it was the de Havilland Comet in the 1950s. They were designing a passenger airplane, and they couldn't figure out why at altitude, these planes kept like breaking up and falling out of the sky. I think 2 or 3 test pilots had been killed testing these airplanes. And like they went and tried to figure some stuff out, and a test pilot took another plane up, and like at a certain like throttle position, the cruising throttle setting, they felt this weird vibration in the plane, and they just couldn't really figure out why it was there. And so the test pilot kind of pulled it back, and the vibration went away, and he put it back to cruise, and this vibration started to happen. His co-pilot looked out the window and saw the wings doing this. Okay? And airplanes don't fly like that. Birds fly like this, okay? What was happening is the engine frequency, the frequency of the propellers, was matching the natural frequencies of the wings. And so resonance built up, okay? And the wings started flexing up and down, and they got bigger and bigger and bigger, just like you pushing kids on the swings. And the wings were ripping themselves off. And they couldn't tell in the cockpit. In the cockpit, it was like, what's that weird vibration? But if they just had looked out the window, they would have seen their wings doing this, right? So the pilot quickly killed it, brought it back in. They redesigned the plane so that. And nowadays, they design like bridges, buildings, structures. They look for the resonant frequencies, and they try to like not match it to things like, say, earthquake frequencies, right? You don't want your amplitude going up in an earthquake. So that's the phenomenon of resonance. And that was all of chapter 10. Okay, so assuming Canvas doesn't crash on you, go away, you should be able to do the chapter 10 homework. We will do we'll start chapter 16, I think it is, on Thursday, right? We're skipping 11. We're skipping all the thermodynamics ones. See you tomorrow for the exam autopsy.